So current and potential difference. We've actually learned about both of these things back in Form 2. Current is arus. Bahasa Melayu ialah arus. So current is where we get our, kalau sini orang Sabah kita panggil karan. So current is where we actually get the dusun word karan. Orang dusun dia bilang, ayah tiada karan, putus karan. So what happened was probably some Sabahan guy long time ago. He heard the British people talking and they were saying, oh, there's no current. And then he went home and then he went to his family. Oh, itu orang putih dia bilang tiada karan. So that's where we got the word for. The other thing is potential difference. Okay, maybe for you, you know this better as voltage. Potential difference and voltage is the same thing. But for Form 5, we'll be using mostly the word potential difference. So electric field. So the concept of an electric field is a very important one. Because the concept of an electric field ataupun medan elektrik, this concept is what helps us to understand the movement of a charge. Right? So we know what a charge is. We know that things have charge. Well, okay, actually, let's talk about that, what a charge is first, because maybe some of you or some of us may have forgotten what a charge is. All right, so charge, we know what a charge, so we know that we have the positive charge and we have negative charge. That is something that we studied way back in Form 2. Positive charge, negative charge. All right. The particle that it has a positive charge would be the electron. Sorry, the proton. And the particle that has a negative charge in the atom is what we call the electron. Yeah, we already studied this in, you studied some of this in chemistry as well, right? So we also study that in chemistry and in other physical reactions, sometimes an electron might move from one atom to another. So when something has more electrons, so let's say you have 3 electrons and 1 proton, then you get an overall negative charge. Right? Just because it's a negative charge, it doesn't mean there are no protons or no positive charges. It's just that because there are more negative, there are more electrons, then it has an overall negative charge. Same thing, if there are less electrons, let's say it loses a few electrons and it has more protons, then we have an overall positive charge. So far, so good. These are things that you already know in Form 1. Now, the unit for measuring charge, we have a unit called coulomb. So coulomb is basically just saying how much charge does something have. Coulomb, or just big letter C. So you already learned about coulomb actually in the past, but maybe we haven't actually gone into this more deep. So we measure the amount of charge that something has by using the unit coulomb. So the more coulombs something has, that means it has a bigger charge, whether positive or negative. Okay. So this is a review of what we learned in Form 2. Now back to the question at hand. Electric field. What is an electric field? So we may not yet understand completely what an electric field is, but we have definitely seen examples of electric fields every day. So these are just a few examples. By the way, you can follow all of this along with your textbook. Most of your notes, this is just what's in your textbook. I just take the most important things and try to condense it and try to make it more as short as possible. So, what are the phenomena that indicates the existence of electric fields in our daily lives? So, things like lightning during a storm, things like a fine stream of water bending towards a charged comb, things like hair being attracted to a charged balloon, tiny pieces of paper to a charged plastic comb, a charged drinking straw moves closer to an approaching finger. Um, and so, some people, so those of you who remember what you studied in Form 2, you might notice that these things seem to be um, very similar to the things that we study in the topic about electrostatic or static electricity, and you will be correct because electric charge is just another word for saying a static electricity actually. All right, so this is what an electric field is. I'll read it around. An electric field is a region around a charged particle where any electric charge in the region will experience an electric force. Now this is the this is the definition given in your textbook. So maybe or probably I should give some explanation. So all right. So the region around a charged particle. So let's say we have a particle. Wait, that's too high. So let's say we have a charged particle. Let's say we have a particle with a positive charge. All right. Now, around this charge, there is a certain amount of area. There's a certain amount of area that where if another electric charge goes in this area, let's say another positive charge. Wait, no. Let's not talk about another positive charge yet. Any other charge that goes in this area will experience some kind of force. So another way we can put this like this. An electric charge has its territory. Ada dia punya kawasan, ada dia punya medan. So I'm just gonna draw some dots line. So let's say this area here within the dotted line ialah dia punya kawasan. And this charge is the king there. If any other charge goes into this area, that means it is now in the area of the charged particle. So if another smaller charge goes in this area, this smaller particle or this other charge will experience a force from the charged particle because this smaller one is in the electric field. This is what we call, remember this area is called the electric field. And so it will experience some kind of force. Now the type of force that it will experience will depend on its charge. So let me go back to the... Alright, so the electric field lines around a positive charge always point outward, while the electric field lines around a negative charge always point inward. Okay, so the way it works is, if we go back to the charge, now we have this charged particle and it has the electric field around it. So if it's a positive one, then within this field there is an electric force pushing outwards. That is the electric force that it has. That is the effect that it has on its own electric field. So for the so we call these lines, these are just imaginary lines, by the way. These are lines that we use to help us imagine it. Okay, so we call these electric field lines. So the electric field lines around a positive charge will always point outwards. While if it's a negative charge, on the other hand, so the same thing, a negative charge also has its own also has its own electric field, but instead of going outwards, this time the electric field lines are going inwards. Alright? So if it's positive, it's going to be pushing out. If it's negative, it's going to be pulling in. Now, why is this important? This is important for us to know because this helps us to understand how different charges interact, how different charges will behave with one another. Okay? Excuse me. So the electric fields around, because this is the important bit. We learned this in Form 2 actually. Unlike charges attract each other, while like charges repel one another. So we already learned this. Positive dengan positive, dia akan menolak. Right? Similar to a magnet. A positive charge and another positive charge will push each other away. A negative charge and another negative charge will also push each other away. A positive charge and a negative charge will pull each other together. So the way it looks like is if we were to draw this phenomenon. So if it was either both positive, or let's draw both positive first. So if it was both positive, all right. So we have, this has its own lines, right? It will be pushed away. Its lines will be pushed away. It doesn't want to meet other positive fields. It's not going to meet, so it's going to be pushed away. All right. Same idea if it's negative. So the electric field lines, if they're both positive, they'll push each other away. Now, if they're both negative, okay, it will be the opposite direction of the arrows, but the result will still be the same, where they will still not want to meet. Okay, they will push or repel each other. So the lines will not meet. Now, if one is positive and one is negative, something like this, and what happens is the electric field lines will combine. The positive, remember, the positive is pushing, and the negative is pulling. And so these two are attracted to each other. In physics, usually opposites attract. This is also the same reason why in chemistry, this is also the reason why chemical reactions occur, because we have positive ions and negative ions, and so positive and negative ions will come together and create new substances. All right, so it's the same reasoning here. So that is what electric fields are and what causes the electric fields. All right, so of course electric fields now, even though every charge has an electric field. Okay, before that, any questions up to this point? Okay, maybe no questions yet at this point. If there are any questions, just go ahead and type. All right, so we've learned what is the electric field, which is the area where a particular around a charge, and if anything comes in that area, they'll experience what we call an electric force, either a push or a pull. Now, assume that a positive test charge is placed in an electric field. A positive test charge means just we'll put in a charge as a test anywhere in an electric field. So this charge, like we've already learned, will experience an electric force, like we just learned. Either it will be pushed away or pulled away depending on the type of charge particle, whether it's a negative charge or a positive charge. Alright? But how strong is that force will depend on several factors. How strong is the pushing or the pulling? It all depends on several things. This is what we call the electric field strength. So generally, where is this? Okay. So generally, so let's have our main charge particle, and then let's put a test charge, another small charge. We call it a test charge because we use this to test how strong is the charge of electric force of the bigger or of the main charge particle, right? And so here we have positive and positive, and so this will experience a pushing force. And so we need to find out how strong that force is. That's what this question is about, electric field strength. How strong is the pushing or the pulling force between these electrons? So we can use this formula. And by the way, there are about, I think, around 4 or 5 formulas in this topic. I'm going to talk about all the formulas today. I won't be doing too many examples yet, but what I want to discuss rather is how we can apply these formulas and the effect of each of the different parts of the formula. Okay, so back to this question here. The electric field strength E at a given point in an electric field is defined as the electric force acting on a unit positive charge placed at the point. In other words, just like this picture here, we have an electric unit positive charge placed at the point. How much is the electric force? This is the electric force here. How much is the electric force acting on the unit positive charge? So how much is it? The formula that we use to calculate that is E, capital letter E, equals F over Q. Okay, so E is electric field strength, or the strength of the electric field. F is the electric force measured in newtons. So how hard is it pushing? Is it 1 newton, 2 newtons, 100 newtons, or 0.000 newtons? Q is the quantity of electric charge, or how much electric charge it is. Right? So the SI unit for E is Newton per coulomb. So for every coulomb, so basically is this. For every coulomb, how many newtons is it pushing? So let's take a look. Let's experiment with this formula a bit. E equals F over Q. So remember, E equals a electric field force. Alright, so F equals the electric force. In newtons, and Q is quantity of charge. Which will be in coulombs, or C. So formula, the normal formula is E, electric field strength, equals F over Q. We can also rearrange it. We can rearrange it to say F equals E over Q. Sorry, that's not wrong. How could I make such a mistake? Bad teacher. Alright, sorry. E Q. So those are two different ways of expressing the equation. So let's look at the first one. So if E equals F over Q, then basically what that means is there are two different things that can affect the electric field strength, either by changing the force, electric force, or by changing the quantity. So, for example, if F remains the same, let's say let's say F is constant, it doesn't change. The only thing that's changing is Q, the quantity of electric charge or the number of coulombs. All right. Which one? And you can answer in the chat. Which one would cause a stronger electric field strength? A higher amount of coulombs or a lower number of coulombs? If F is always the same, which one would cause a stronger electric field? Higher number of coulombs or lower number of coulombs? Right? Yes, so if we think about it as a fraction, a lower number, because let's say F equals 1. Okay, I am running out of space. I'll use the backside for now. So let's say let's say F equals 1. Let's just assume F equals 1. So E equals 1 over, let's say, Q. If Q equals, let's say, 2 versus Q equals 3. 1 over 2 is bigger than 1 over 3. Right? 1 over 3. So one way for us to make the electric field stronger actually is to reduce the number of coulombs per force, right, in this equation. So in other words, how do I put it? The less coulombs I need per Newton, because remember this is on the top is counting force. The less coulombs I need per Newton, that means the stronger the electric field force. On the other hand, if we were to look at this time, let's say that Q, on the other hand, if Q is constant, let's say ini Q ni tidak berubah. Let's say Q is 1. Okay? And on top is F. F is the force, and this time we will change the amount of force. Okay, I think this is quite obvious. If the force is higher, then the overall electric field strength is also going to get higher. And so the reason I'm talking about this is because this is actually what's important in physics. Your ability to look at each part of the equation. Ini kamu mesti boleh buat. Kamu kena lihat setiap bahagian dalam equation and think. Kalau saya tukar satu, apa yang berlaku kepada yang lain-lain? You need to be able to think that in physics. That is as important or even more important than your ability to just count the formula. Because if you watch, kalau kamu tengok dia punya seminar, dia bilang actually, dia cakap macam ni. Untuk physics form 4, form 5, dia punya tahap math sebenarnya masih tahap yang sangat rendah berbanding actually even compared to what you study in school, additional mathematics. If we're talking about mathematics, additional mathematics, the mathematics in AdMath is at a higher level compared to the mathematics in physics, right? But what makes a lot of students fall down is this. They're not sure how to look at the formula. They don't think, okay, kalau saya tukar satu, apa yang berlaku kepada nilai-nilai yang lain? Or how does it affect the other values? Now, on the other hand, if we were to write the formula like this, F equals electric force times force equals the electric field times the coulomb, then we can think, all right, how does these two things affect the amount of force? So we can tell that if you increase either one of these things, sama ada kamu kasih makin besar ini E ataupun kamu kasih makin besar ini Q, both of these things, either of these things will cause the force, the total force to increase if the other remains the same. So if we have a higher amount of Coulomb, higher number of Coulomb, but the same electric field strength, then you'll have a higher force in total. Or if you have a higher amount of electric field strength and the same number of Coulomb, same amount of charge, you still end up with a higher force. And so these are all the things that we have to consider when we are talking about electric field strength. Yeah. All right. So the SI unit for electric field strength is, I talked about this just now, is Newton per Coulomb. In other words, for every Coulomb, how many newtons how many newtons of force is happening? So if the electric force, you might say 5 newtons per Coulomb, which means if the charge is 1 Coulomb, it will be 5 newtons of force. If it's 2 coulombs, it will be 10 newtons in total. Right? So this is electric field strength. Okay, so write that formula down, although it is in your textbook. Oh, by the way, before I forget, another thing that was mentioned in the seminar. If you are asked to give the definition of something, let's say in this dalam soalan nanti dia tanya, what is the definition of electric field strength? Okay, you should write this down. You should write electric field strength is the electric force acting on a unit positive charge at the point. You cannot, because I know there are some students who like to do this, and in the past I have accepted this, but you cannot write down the formula. You cannot just write down the formula as the definition, because that's not what a definition is. You need to write it out. You need to write down the sentence, and you need to write down all the important keywords in the sentence, right? You might be able to change a few words. For example, the electric force on, and you might be able to say the electric force on a unity positive charge placed at the point or at a certain point. You might use those words, but you still need to get the overall meaning. But what you cannot do is you cannot just write this formula as your definition. You cannot use a formula as a definition. You can use a formula to help you remember a definition. You can use the formula when trying to calculate things, but you cannot write the formula as a definition. That's very important for you to remember when you try to answer these questions later. All right. Any questions so far? Okay, no questions at the moment. I will continue. Electric field strength produced by 2 parallel charge plates. Okay, so I'll have to explain this a bit. If you have your textbooks, you can see what I'm talking about. But if you don't, then let me just quickly draw a picture for you. So in some experiments, what they do is that they will use plates that each have its charge. So we have plate 1. So usually plate 1, and then we have plate 2. Usually they'll use positive and negative, but in theory, it could also be both positive, but never mind about that. So we have 2 plates, plate 1 and plate 2. Okay, and the plates are charged. And there is an electric field because they are charges. Each of these plates have its own electric field. And so we have the interaction between the 2 plates. And so, in this case, if we were to try to find the electric field strength, we can also try to find the electric field strength between in the middle of these two charge plates. So if that is the case, then we have a slightly different formula that we use, which is this. E, so E equals electric field strength. Electric field strength equals to V over D. So V equals potential difference between two parallel plates measured in volts, and D equals the distance between the two parallel plates in meters. So in this formula, the SI unit is volt per meter. So, example. So if the potential difference between these two plates is 5 volts, that's too high. So let's say the potential difference is 5 volts. And the distance between these two is, let's say, 50 centimeters. No, let's make it smaller, 10 centimeters or 0.1 meters. Then our electric force, remember E equals V over D. 5 over 0.1. So we get an electric force of, rather the field is 50 volts per meter. That's the strength of the electric field. Okay, now it's a similar thing. If we were to talk about the formula and we were to look at how the formula affects each other, E equals voltage over the distance. If we increase the distance between the two plates, then just based on the formula, automatically the electric field will get weaker. I mean, that makes sense lah kan. Kalau dia semakin jauh, then dia punya force ataupun dia punya kebolehan untuk menarik pun tidak begitu kuat lah. Because it's getting further away from each other. But you need to be able to see that from the formula. At the same time, if the distance is smaller, meaning to say the two plates are closer to one another, then when they're closer to each other, you end up with a higher electric field strength, right? Or the voltage. Of course, the higher the voltage, even if the distance is the same, the higher the voltage, then of course overall the higher the overall electric field strength. Conversely, if we were to compare the two things that were further and closer to each other but has an equal amount of voltage, if it's further away yet still manages to have the same voltage, then the electric force must be higher. Or if it's closer but it still has the same amount of voltage, then the electric field must be smaller. So we need to think about how these different factors affect one another. Alright, so back to that slide. So the SI unit for this formula is volt per meter. However, we can directly convert Newton per coulomb and volt per meter, in the sense that 1 Newton per coulomb is exactly the same as 1 volt per meter. It's equal, or it's equivalent to each other. All right. Electric current. Okay, any question on before that, any question on electric field strength? Okay, none at the moment, maybe later. All right, so electric current. So we already learned about current way back in Form 2. Of course, in Form 2, maybe we use the Malay word for current, which is arus. So, kamu sudah tahu lah, arus ialah, okay, current only exists when there is a flow of charge. Arus tu hanya berlaku bila ada aliran cas di dalam 1 liter. Maksudnya, kamu hanya boleh ukur arus di dalam liter yang lengkap. Kalau tidak ada liter yang lengkap, I don't care how big the voltage is, kalau tidak pengaliran cas, there is no electric current. Okay? Now, considering that, kalaulah kamu ada sudah dia punya electric current, okay, considering if you already have the electric current, then how do we calculate that? Or what is current? Or how do we define electric current? So current, and we use the letter I as the physics symbol. I equals QT. Now, what we learned actually in Form 1 that I equals voltage divided by resistance. That is still correct. But that's only in relation to voltage and resistance. Okay? Here, what we're talking rather is current in relation to the number of charge or the amount of charge. Okay? The one that we learned in, well, actually, no. So, what we didn't learn in Form 2 is actually current is telling us how many coulombs is flowing per second. That's the kind of important thing that we did not discuss back in Form 2. So, the formula given is I equals QT or Q equals IT. Sorry, I equals Q divided by T, Q over T, or we can also restate it as Q equals IT. So either we can use the first one to decide or try to calculate the electric current or how much current is flowing in a second, or we can use the second one to figure out what is the total charge of something. So I is current, Q is total charge measured in coulombs, and T is time in seconds. Both capital letter Q and small letter q is usually charge, coulombs. T will be time in seconds. So SI unit for current, I is coulomb per second or ampere. So coulomb per second or ampere, these are both the same things. It's just that in Form 1 and Form 2 we usually used ampere, but you can also use coulombs per second. So how many coulombs is flowing every second? That is what current is. Again, if we take a look at the... Oh, sorry. Why is Q used to represent charge? I don't know. I mean, it's funny because in physics, every quantity, every type of quantity has a letter or a symbol, right? So, for example, H is always like G is gravitational acceleration, T is time, D is distance, L is length, and different symbols. So for some reason they chose Q for charge. Why exactly? I'm not sure. But yeah, Q is what they use for charge. Why exactly? Yeah, I'm not sure exactly why. I'll have to check on that. Maybe if I read up, maybe I'll find something. But at the moment, I don't really know why they choose Q. All right. Anyway, where was I? All right. Yes. So I equals the total, the current, Q equals total charge, and T is time. Right? So if we look at how they affect each other, okay, if we have a higher total charge in the same amount of time, then obviously it will cause a higher current. Of course, more coulombs per second means more current. At the same time, if we have the same amount of charge but we manage to move it faster in less time, a smaller number, then the overall effect is the same. We still get a higher total current. Q equals IT, same thing. Okay, if we have a high current, even though it's only 1 second, you still get a very high total charge. If you get, or if you increase the time, let's say you let a circuit run for 1 minute, so 60 seconds. Okay, then you'll get a total overall charge that is higher. I have 3 more slides left. Okay, potential difference. So this is the last concept that we will talk about for, I think this is the last concept that we'll talk about today. Last or second last. So potential difference. If you don't know what the word potential difference is, just a fancy word of saying voltage. Okay, in Form 2, I think the exact definition is voltan ialah beza upaya di antara dua titik. Beza upaya or potential difference. What is the potential difference between 2 points? So the question here is what makes the current flow in a circuit? This is due to the electric potential difference. So current can flow from one point to another due to a potential difference. That's a wrong spelling. That's a typo, I should say, between the 2 points in a circuit. So when we have a circuit, we usually have a battery. Usually the battery, we give a battery rating of 5 volts. And then we have the positive side and the negative side. And we connect the circuit like that. What this 5 volt means is that the difference between these 2 points is 5 volts. Or the potential, beza upaya, exactly. The potential difference is 5 volts. Now why is this important? Imagine, so the way for you, so for a way for you to imagine is bayangkan kamu ada 2 tangki. Right? Bayangkan kamu ada 2 tangki. Okay, satu tangki lebih besar berbanding tangki yang satu. So let's say we have a tangki that's about this tall and a tangki that's maybe about this tall. Right? Now, because of the laws of physics, yang lebih tinggi akan mempunyai tekanan ataupun pressure yang lebih tinggi. We just learned about pressure in the previous chapter. So the higher tank will have a higher pressure than the lower tank. Because of the difference of pressure between these 2 tanks, kerana beza tekanan di antara 2 tangki ini, kalau kita kasih sambung satu pipe dari tangki yang satu ke pipe yang satu, what will happen? What will happen is water from the first tank that has more pressure will go to the tank that has lower pressure. That is just simply a law of physics. Usually things go from high pressure area to a low pressure area. It's the same thing for air. It's the same thing for air. Air moves from a higher pressure area to a lower pressure area. So we can think of the potential difference as electric pressure. In fact, some people use the word electric pressure. Electric pressure, in which if there's a greater difference between the electric pressure or a greater difference between the 2 points, then you have more capability or a higher chance of a lot of current happening. That's why we remember in Form 2, if you have a higher voltage, usually that will also result in a higher current or more flow because there is more pressure, electric pressure. So that is a simplified way of saying a simplified explanation. Now, the potential difference V between 2 points in an electric field is, if we go by the textbook definition, is the work done W in moving one coulomb of charge Q to one point, from one point to another, or moving one coulomb of charge Q between 2 points. So if I were to draw it, or rather if we were to use this picture that we already have, so this is point 1 and this is point 2. Now to get one coulomb from here to here, to move one coulomb of charge, how much work is done? How much work is done? How much work is done by moving one coulomb from here to here? That is what voltage is. That is what potential difference is. If the potential difference is very low, then maybe from here to here, you only do about 1 joule or 2 joules. But if the potential difference of the electric pressure is high, then from one point to another point, you might generate 12, 15, 20 joules, more joules. Okay, work is measured, by the way, in joules. Or the SI unit for joules is J. So if we go look at the formula, the two formulas is very similar. Okay, these two formulas are more or less the same. Yeah. So V is potential difference or the voltage. All right. W is work done, or you can use E, energy transferred. Practically speaking, the question will be the same, because both work done and energy transferred is measured in joule. Yeah. Sometimes you see the word energy generated, or amount of energy used, or amount of energy moved, or the amount of work done. These all mean the same thing, the amount of energy. And Q is the amount of charges flowing. Q, in other words, how many coulombs is flowing, right? So of course, if we have, again, let's look at how we can affect the formula. How does the different things in the formula affect each other? So if V equals, so if V equals WQ or EQ, then we can think, how do these different factors affect the voltage? So of course, if moving one coulomb uses a lot of energy, increasing the amount of energy transferred or increasing the number of joules, of course, that will naturally increase the voltage. At the same time, if we reduce the number of coulombs flowing per, this is important, per joule. So for example, we have one circuit where for every joule it moves three coulombs, and another one, for every joule it moves 1 coulomb. The one that has a lower coulomb count or number of coulombs will have a higher overall voltage. Or we could rewrite the equation as E equals VQ, or W equals VQ. Okay, so higher voltage equals a higher voltage, and higher amount of coulombs will equal to higher amount of energy being produced. Low voltage or lower number of total charge or coulombs will produce lower amount of energy. So the potential difference, the SI unit for potential difference. V is joule per coulomb or volt. So these both mean the exact same thing. So the potential difference is 1 volt if the work done to 1 coulomb of charge from one point to another is 1 joule. So this is how you think of it. If it takes 1 joule to move one coulomb of charge, then that's 1 volt. If it takes 1 joule to move 2 coulombs, then that's 2 volts. If it's 2 coulombs, if it's 2 coulombs per 1 joule, that means the voltage is 0.5. If it's 2 joules per 1 coulomb, then you'd get a total of 2 volts. So yeah, this is how it all affects each other. Just as an aside, I forgot to put this in the slide, but in some questions, I want to talk about a little bit about coulomb. So what is coulomb? So coulomb, like I said, is a unit for measuring charge. Charge, as we already established, is determined by the electron, usually determined by the electrons. How many electrons did it gain or did it lose? Right? So, but coulomb is not counting exactly. It's not exactly 1 coulomb equals 1 electron. No, we could try to count all the electrons, but then that would be impractical because there are thousands and thousands of electrons and they are very small. So we have an equation. We have an equation where we can calculate the charge of an electron. We know that the charge of an electron. This is actually in your textbooks, but I'm gonna go ahead and write down. Charge of an electron, small letter e, is 1.6 times 10 to the power of negative 19 coulombs. So the charge of 1 electron is actually very small. So for 1 coulomb, 1 coulomb is actually equivalent to 6.25 times 10 to the power of 18 electrons. Yes, exactly. So coulomb is similar to mole in chemistry. In chemistry, you use mole to help you calculate. Okay, if you have 1 mole, then compared to the atomic number, then 1 mole of this substance will produce this many grams. Yes, and coulomb we use, and we also know that coulomb also. Mole tells us that okay, this 1 mole has this many atoms, right? But it's not like 1 mole equals 1 atom. No, it's just a unit for us to measure it. Coulomb is the same thing. So like what Henry said, coulomb, yeah, it's similar to mole, right? So 1 coulomb equals 6.25 times 10 to the power of 18 electrons. So if you find a question that asks you, okay, how many electrons are flowing, for example, are flowing through the circuit, or how many electrons does it have, then you need to use this formula. Meaning to say, what you need to do is you need to find the number of coulombs first, then you need to convert the number of coulombs into number of electrons. I think there are a couple of questions in your textbook that ask you to solve that. But other than that, yeah, so that's it for talking about all the different formula. And so sometime later, then we'll get into the application of all this formula sometime later. I want to get through all of this I want to go through all of this for now, because I wanted to I'm trying to get through the book as fast as possible, guys. We all know that we're probably not going to go to school anytime soon. So yeah, we need to try our best to finish the textbooks. Okay, any questions? Any questions you'd like to ask regarding charge? Sa bilang sekolah, I don't know.